Welcome back! Today, we're going to tackle a classic coding challenge that's all about finding hidden patterns in data. It's the kind of puzzle that pops up in surprising places, like trying to spot a trend in the stock market or even analyzing sequences in DNA.
All right, let's just dive right in. Imagine someone hands you a complete jumble of numbers and says, find the longest strictly rising trend you can. Sounds kind of simple on the surface, right? But the real trick is figuring out how to do it efficiently.
I mean, just look at this array. The numbers are all over the place. We start at 10, drop to 9, then way down to 2. Then we jump all the way up to 101, and then plummet back down to 18. It's not at all obvious where the pattern is. But if you look closely, hiding in plain sight, there is a clear upward trend. You can pick out the 2, then the 3, then the 7, and finally the 101. That gives us a beautiful sequence with a length of 4. So the real question is, how do we get a computer to see that?
Okay, first, let's get the rules of the game straight. We're looking for a subsequence. And this is a really important detail. It means we're allowed to skip numbers. We skipped the 10 and the 9, for example. But the numbers we do keep have to stay in their original left-to-right order. No rearranging allowed.
All right, let's look at our first attempt. This is a really clever and pretty intuitive method called dynamic programming. If you haven't used it before, it's basically a powerful way to solve big problems by breaking them into smaller, easier-to-solve pieces and then building up from there.
The whole idea here is that we're going to build up our answer step by step. For every single number in our list, we're going to ask a simple question. What is the longest possible increasing sequence that ends right here at this exact number? And to answer that, we just look back at the answers we've already figured out for all the previous numbers.
So, first things first, we create this new array. Let's just call it f, and it's the exact same size as our list of numbers. We fill it up with ones. Why? Well, because every number, all by itself, is an increasing subsequence of length 1. It's our starting point.
Okay, now this is where the magic happens. Let's look at the number 5. To figure out its value in our f array, we look back at every number that came before it, 10, 9, and 2. We ask, which of these are smaller than 5? Well, only the 2 is, so we go look at the value for 2 in our f array, which is 1. That means we can take that sequence of length 1 and just tack our 5 onto the end. So 1 plus 1 gives us a new length of 2.
And this is a perfect example of the process. When we get to the number 7, we do the same thing. We look back. We see 2, 5, and 3 are all smaller than 7. Okay, so what are their lengths in our f table? Well, the sequence ending in 2 has length 1. The ones ending in 5 and 3 both have a length of 2. We always want to build on the longest one possible, so we take the max of those, which is 2, add 1 for our current number 7, and we get a brand new length of 3.
So, after we've gone through every single number, one by one, and done this calculation, this is what we're left with. Our f array is completely filled out, and each number in it tells us the length of the longest increasing sequence that ends at that specific spot. To find our final answer, all we have to do is find the biggest number in this whole f array. And boom, there it is. The biggest number in our f array is 4. We found our answer, so we've solved the problem. But have we solved it efficiently? That's the real question. And that question brings us to a bit of a plot twist. For a tiny list of 8 numbers, our method works great. But what happens when that list isn't 8 numbers long? What if it's 8 million?
See, that first approach has what we call a time complexity of O(n) squared. Now, n squared is just a formal way of saying that the amount of work our computer has to do grows exponentially. For every number, we have to look back at all the previous numbers. So if you double the size of the list, the time it takes to get an answer roughly quadruples. For huge lists, that can become painfully, unusably slow.
And this is the classic follow-up challenge. Can we do better? Is there a faster way? One that doesn't slow down so dramatically as our list gets bigger? Honestly, this is where computer science gets really, really cool. The hunt for a smarter way.
And the answer is yes, we absolutely can do better. So let's move on to a much faster solution. This new approach completely avoids that expensive look back at everything step by using a really powerful data structure as its secret weapon.
Say hello to the binary indexed tree. Let's go back to our filing cabinet analogy for a second. Our first method was like opening every single drawer one by one to find the best file. A binary index tree is more like a magic, self-organizing filing cabinet. It cleverly keeps track of the best result in whole sections of drawers. So when you ask it for the best file, you don't have to check every single one. You just check a few of these section summaries and you get your answer almost instantly.
So what does this actually look like? Well, first, we do this little trick where we rank all our unique numbers. So 2 becomes rank 1, 3 is rank 2, 5 is rank 3, and so on. Then, as we go through our original list, let's say we get to the number 7, instead of scanning everything that came before it, we just ask our magic tree, hey, what's the best length you've recorded for any number with a rank lower than 7's rank? The tree instantly tells us 2. So we calculate our new length, 2 plus 1 is 3, and then we tell the tree, okay, update your records. The new best length for a sequence ending at this rank is 3. It's more of a conversation with our data structure than a manual search.
So we've just seen 2 totally different ways to solve the exact same puzzle. One is very direct and methodical, and the other is way faster, but also a bit more abstract. So how do they really stack up against each other?
Let's put them side by side. On one hand, you've got dynamic programming. It's super intuitive, right? You can almost trace it with your finger. It's clear. But its O(n squared complexity means it just grinds to a halt on big inputs. On the other hand, the binary index tree approach is much, much faster at O(n log n because it uses that special structure to find the best previous result instantly without that slow, full scan backward every single time. But you know what's cool? It doesn't matter which path we take, the scenic, methodical route, or the high-speed expressway. Both of them lead us to the exact same correct answer. The length is and always will be 4.
And that leaves us with a final, bigger question, one that goes way beyond this one problem. While the faster, clever O(n log n solution is technically better for massive amounts of data, the simpler O(n squared solution is often way easier to write, to understand, and to fix if something goes wrong. So if you were building something for a real project, which would you pick? When does pure speed actually outweigh the value of simplicity and clarity? That's a trade-off